Sorry, I forgot to do recording. Okay, good morning. In fact, so today we will have some tutorial problems on learning properties of fluid. So for the properties, we know there are many properties of a pure substance. However, we have to understand when our system undergoes a thermodynamic process, there is a state change, okay, change of state, change of properties. And most importantly, in fact, because for our focus, heat engines, okay, in fact, the working fluid usually, because when the working fluid undergoes phase change, so large amount of heat will be absorbed or rejected. So we have to understand, especially during phase change, what will happen, what's the change of properties during phase change. So for example, we have learned that if for all diagram, we have different diagram. In fact, in the future, we understand there are several common diagrams for us to learn. One is pressure volume, okay? Then is the pressure enthalpy, and also temperature entropy. Okay, so even on a temperature entropy diagram, so we can see any pure substance with such shape curve. So what does it mean? So it is mean if the fluid, okay, if here is a fluid, is a liquid, if the liquid properties in this region is unsaturated or is compressed, and then what about here is wet region, okay, it's wet region. So for wet region, it means the liquid and vapor are saturated. So here is a mixture of saturated liquid and vapor. And what about here? So these two are very special because they are the properties, they are the state of saturated liquid state and saturated vapor state. And here is the mixture of saturated liquid and gas and vapor. Okay, then what about here? It's superheated, okay? Then it's superheated. It's superheated. So for us, if we with the given properties, we want to know if it's compressed or superheated, or if it's a mixture, then we have to check from the table. I have provided you the tables and the diagrams of common fluid such as water vapor and common refrigerants. So then you need to identify, so the state, define the state of the working fluid in the system, if it's superheated or it's dry saturated or wet saturated or it's compressed. If in the wet region, however, because our fluid undergoes heating, cooling, so in the wet region. So in the wet region, we have to learn, we have introduced one term, is dryness fraction. Okay, dryness fraction. Is dryness fraction. So definitely, besides we learn do the analysis of properties, we also need to understand for all the processes. So what's the meaning for that process? And especially in the wet region. Okay, for example, the dryness fraction, if here the dryness fraction is 0, okay, it's 0. And then here is 1 dryness fraction. This is the meaning, the mass of dry vapor. Okay, so now let's read question number 1 first. Okay, for question number 1, we can see is for process in a steam turbine. So it's a steam turbine, and the steam. Firstly, we want to know if the steam at 4 megapascal and temperature 500 degrees Celsius, then where it is. Okay, now we need to check from our saturation table. So please let me know. Okay, 4 megapascal. What is the saturation temperature? Okay, please let me know. Check from the table. Okay, if water steam is at 4 megapascal, what's the saturation temperature? Please type your answer here. Okay, you cannot wait for me. I'll ask you to find out the... Okay, anyone get the answer? So if for water steam at 4 megapascal, what's the saturation temperature? Okay. Yeah, you need to check the table to find if for water steam is 4 megapascal, what's the saturation temperature? Because we want to know the table I have shared with you. So under the folder, even I just check from my computer now. Water steam. You know, yesterday, last lecture, I asked you to learn how to use the tables and the diagram. Okay? Even for our example, I ask you to check. Okay, please use the table I think I have shared with you. Let me check again. I didn't share with you. Okay, let me see. Okay, now you can download. Okay, then maybe I share here. Okay, so for the table, firstly, we find from the, okay, you can download from the folder you can download the file from our folder. Okay, so if it's a 4 megapascal, then the pressure is 40 bar. Then this is the saturation temperature. The saturation temperature is 250.3 degrees Celsius. So therefore, for the given conditions, it's 500. So it's larger, okay? 500 is larger than the saturation temperature. So therefore, it's superheated. Okay, so we understand that in fact it's superheated. It's superheated, and then it enters an adiabatic turbine. Adiabatic turbine. That means okay. The heat transfer flow is 0. Okay, no heat transfer if it's called adiabatic turbine, and also it's expansion process. It's expansion process. Using the steam water tables, considering two cases. If it's a reversible process and irreversible process. So we are using for a reversible process. So we can define, so for the two cases and reversible process. So first one, if it's a reversible process, then if it's reversible and adiabatic, then it means it's entropy is isentropic process. Isentropic process. If isentropic process, that means the specific enthalpy will be equal. Okay. So for the first isentropic process, the entropy of state 1 is equal to the entropy of state 2. Then now let's have a look. So we want to know the process on the diagram and indicate the area which can represent the power output for the two processes. So for first state, we have defined is superheated. then we want to know where the state 2 is can be here because we know the pressure. However, if it's wet, is expansion or is dry saturated or is still superheated, we don't know. So therefore, we need to do the calculation. Okay, let's see the results. So first, from the tables I provide you, we know state 1 is superheated. What about state? What about, and also we get is specific enthalpy. And for state 2, we don't know if it's wet in wet region or not. However, we understand that, and also for state 1, we know these two figures. Okay, one is enthalpy and is entropy. So because we know isentropic process with the same entropy, so we want to see this entropy is larger or smaller than the dry saturated water vapor entropy. So we can also find from with if the state at 0.4 bar, okay, is and the entropy for saturated vapor. Okay, so because this one is greater, so therefore we know it's wet. Okay, it's in wet region. Okay, in wet region. And also accordingly, then we will calculate. And so if it's in wet region, then it becomes difficult because if it's in wet region, it becomes difficult because we need to calculate its dryness fraction. Okay, so similar from the table, we can find we can find all other specific entropies. Okay, so maybe we work on it again. So show you how to find. Okay, so for the entropy of state 2, and from the table we can get so for wet saturated liquid, saturated vapor. Okay, and then we calculate the dryness fraction. So it's approaching dry saturated. Then we can calculate the enthalpy of state 2. Okay, so then we want to calculate. We also calculate the power output. So for the wind turbine, so for the steam turbine, because it's open system, then we got the first law equation for the steam turbine. Then we think the kinetic energy differential and the potential energy potential can be ignored. So, and also we know because it's a adiabatic process, so the heat flow is 0. So we can get the work output is directly the change of enthalpy. So we can calculate. So it's a negative minus. So that's meaning is expansion. Okay, it's expansion. So it's work output. Okay, so this is for the first. However, for the second question is regarding its irreversible process. However, there is a definition of its efficiency. So as I have mentioned, reversible process usually using for reference. And then accordingly the work output is also the difference of the pressure. The work output can be also calculated similar to the following the first law equation. So we can get the work output is also equal to the enthalpy difference. So we can calculate this value. Okay, I think I leave you several 5 minutes on this question. See if you can you learn how to use the tables diagram. So go to the folder, go to our folder to check if you understand. So firstly, for this question, we need to know the state. Where is state 1? Is superheated. It's superheated. Then for state 2, if it's isentropic process, then isentropic process. Okay, isentropic process, entropy are equal. Okay, and we want to know if it's wet or no, if it's here or it's superheated. Then we compare this entropy with the point of dry saturated and wet saturated fingers. Then it's between them. So we know it's in wet region. Okay, in wet region. And also we calculate the dryness fraction. It's 0.912. So therefore, we can see the point here, and we can find the state of state 2. So it's pressure with its pressure and the dryness fraction 0.912. Okay, and so for the following the first law expressions for open system, we find in fact then the value, in fact, the work output is equal to the change of enthalpy. Okay, change of enthalpy. Then we can calculate the work, the turbine work for the isentropic process. And if irreversible, so we got efficiency. So we got the efficiency of the here is the here is the actual one, so this is the ideal one. So then we can get the for actual one. So we can see it's superheated. In fact, because we can compare with we can calculate its enthalpy. Okay, we can compare this enthalpy with those critical saturated points. If it's larger than the one of saturated vapor, so it's superheated. Okay, we draw superheated, and then we got the actual process, and the shaded area can represent the work. So the work output, in fact, sure, is smaller. To be honest, I think this from textbook is not correct. Okay, here we're using the dotted curve, and also the shaded area cannot represents the actual work. Okay, so be careful with it. Okay, and maybe I'll leave you because I'm not sure. Most students are not attending, so I'm thinking maybe next week I will show you the video, and then I get some time for question and answer together. Because I found maybe most of you will choose watching the recording. So I'm thinking in the future tutorial session, the first tutorial session, so we will have our recording. And for second session of tutorial, I will I will be here, but I will not instruct. But I'm here to answer your question. Okay, do you have any question? For question number 1. Okay, so if you don't have any question, because I think most of you maybe prefer the recording, and so at your own time. So now if you don't have any question, then we will work on together on the problem number 2. Okay, I give you 2 minutes to read through the question. Okay, so now let's work on example number 2 together. For example number 2 is also regarding a heating process. In fact, it's a heating process. And we can see the properties will change during a heating process. So we can see from wetted to superheated. Okay, now let's have a look. Firstly, with the given conditions, is 1 kilogram of steam at 7 bar, and also we know its entropy. So I think firstly we need from our table water steam table, we found that at 7 bar, the specific entropy of dry vapor is 6.709. So this figure is larger, okay, than the given entropy. So therefore, we think it's in wet region, okay? It's in wet region. Then it's in wet region. So if it's in wet region, then we want to know it's if it's in wet region, usually we need to calculate dryness fraction, so we can derive other properties accordingly. Okay, so then we calculate the dryness fraction. Okay, in fact, this value is approaching the dry vapor. So therefore, in fact, this is showing not very accurate. Okay, should be here. Okay, should be here. Is approaching. State 1 is approaching the dry vapor. And then, so we define state 1, we know is in wet region with the dryness fraction 0.955. And so it is heated reversibly at constant pressure until the temperature is 250. So we also check from the table steam. So if for the 7 bar, what the saturation temperature? Okay, now let's have a look. What's the saturation temperature? 7 bar. Okay, 7 bar is here. We can get all the data here. Okay. So we can see for 7 bar, the saturation temperature is 165. 165. Okay, this is the saturation temperature. So, and we know that the 250, okay, is larger. Is larger than the saturation temperature. So we know that for state 2 is superheated. And also from here, we can find the specific entropy of dry vapor and saturated and specific entropy of wet saturated liquid. So in fact, by using the water steam saturated table, in fact, we can find all values on the saturation line. So therefore, first we define state 1 is here. Okay, is here. Then we know state 2 is saturated, is superheated because its temperature 250 is larger than the saturation temperature 165 degree at 7 bar. So it's superheated. And then from the superheated table with the given condition 7 bar and 250, we find its entropy. And usually, and following the equation, so we know the heat flow will be usually for open system. No, this is didn't mention. So it's it's open system at constant pressure. So it's the for one element. So for one open system, so the heat flow is equal to the change of entropy. So we can find its entropy. Then we calculate. So for state 1 is the So for state 1 is in the wet region, and then we can calculate for this heating process, it absorbs heat, okay, of 286 kilojoule per kilogram. So this is for this question, and then we can see this is the process line, okay, heating process, and the shaded area. So let's further understand if on the temperature entropy diagram. So for the reversible process, okay, thank you. For the reversible process, then with the reversible process, then the shaded area under the process line is the heat flow, it's a heat absorption or heat rejection. Okay, so I give you 3 to 4 minutes to read question 2 and see why is here, why state 1 is wet, why state 2 is superheated, and if it's to also we have to understand if it's in wet region. First step, we always need to define. We usually need to calculate the dryness fraction. Okay, I think this state 1 is approaching the dry saturation line. Okay, 3 minutes. Okay, I think at the moment, no question from you. Then let's work on question number 4. Or is number 3, okay? So for question number 3, for question number 1, we can see is for expansion process. And for question number 2 is a heating process. A heating process at a constant. A heating process at constant pressure. Okay, a heating process at a constant pressure. Then for question number 3 is also regarding so we can see it's expansion or compression process is reversible adiabatic process, or it's also called isentropic process. So this is usually for compression process or expansion process for isentropic process. So for question number 2 is a heating process at a constant pressure. So now let's read the question. So if a steam at 100 bar, okay, and with temperature 375 degrees Celsius, it expands isentropically in the cylinder behind the piston to a pressure of 10 bar. We calculate this expansion process. What's the work done? So firstly, we sketch the process on the temperature entropy diagram. So we always remember there is a saturation line. But however, we want to know, although we know that this is the constant pressure line. Okay, this is the pressure at 100 bar. Okay, 100 bar. Beautiful. So these are I draw the constant line. Okay, 100 bar. However, although we know the pressure is 100 bar, but we don't know where is the state 1, then we check from the table. Okay, for 100 bar, what's the saturation temperature? Anyone check for me? Okay, I check. 100 bar is 1311. Okay, then is 311. The saturation temperature from the saturated table is 311 degrees Celsius. So look at the temperature, 375 degrees Celsius. It is larger. So therefore, state 1 is superheated. Okay, the first step is always we need to, based on the tables and the given conditions, we need to define the state. So we want to know the state is superheated, or it's wet, or it's compressed. Okay, then we calculate for this is isentropic process. It will be done to pressure of 10 bar. Okay. And then what we want to calculate the work. Then, because the process is adiabatic, so no heat flow. So for this, in a cylinder is closed system, so we need to calculate the entropy difference and the internal energy enthalpy difference, and also the through the first law. According to first law, for closed system, okay, for closed system, we need to calculate, then we derive that for adiabatic, no heat flow, so heat flow is 0. Then we calculate the change of internal energy will be the will be the power down during this process. Okay, then at state 1, we find that it's superheated. Then from the superheated line, we can get the from the table we can get the properties of entropy, specific volume, and enthalpy. Then we can calculate the internal energy of state 1. Okay, by this definition formula. Then we need to calculate where is state 2. Okay, if it's vertically, because there's no change of entropy, so it's vertically down to 10 bar. Okay, at 10 bar, we can find from the tables the value of specific entropy. So at 10 bar. Okay, then we found from the actual entropy. Okay, it's smaller, so here is in wet region, so we can show here is state 2. So for state 2, we can calculate its dryness fraction. Okay, based on the dryness fraction and based on the from the table, the internal energy, we can calculate the internal energy at state 2. And then accordingly, we can calculate for this process. The work done. So we can say this is an expansion process. So it's work done by the steam. Okay, we can get the results. So this is for today's tutorial session. I found that the attendance rate is low. So, and I think it maybe Chinese New Year is approaching. So, and also you have your own schedule to study. So, anyway, today I will stop our recording now. And for next tutorial session, maybe I just show you the video, but I will be here in the room to answer your question. Okay, I will stop recording now, and we still have a few minutes. So see if you get any question on today's tutorial problems. To summarize, for today's tutorial session, we try to learn how to find the properties from tables and diagram, and how to define if a state is superheated or is wet, is in the wet region, or is dry saturated or wet saturated. And then for any thermodynamic processes, okay, if we can define the states, initial state, final state, we can calculate. So for that process, what's the heat flow, or the work done or work input for that processes. And for those processes, if the state is in the wet region, we need to calculate dryness fraction. Okay, dryness fraction usually almost be asked to for calculation. So that's also in the future for in-class test, for examination, when we concern the properties of a state, because it's special, because we also have phase change. We have the wet region, the mixture, the saturated mixture of saturated liquid and vapor. So we always need to calculate dryness fraction. I do wish all of you can spend some time on the tutorial problems and do the calculation step by step by yourself. to find the fingers by yourself. Okay? Thank you.